Now that we have the blast and the revolve taken care of, we're going to be working on symmetric effect to add to the overall shot. So I'm going to hide these. I'm going to create a new geometry container. We're going to call this dev electric. I'm going to change the name to V to green. So these won't be, it's kind of a lightning effect, but more of a much smaller scale. And because this is kind of a robot, being hit by a blast of energy is causing some short circuits and some kind of electrical energy to be discharged here and there. The way I'm going to be doing this, let's dive inside, let's hide everything, and let's get the robot geometry first. So let's, as usual, get robot. I'm going to grab it from here. So I'll dive inside, and we can grab the last one. It's fine. Put it here, and we have our robot. Let me get away a bit. Let's choose a frame, something like this. It's good enough. Time shift. The reason I'm gonna hold this frame is just because it'll be easier for us to see what's happening and for me to explain as well, I guess. So pretty much the way I'm gonna be doing this is we're gonna be creating some particle simulation. So we'll have a particle simulation that's gonna be emitting particles on the surface, and we want those particles to kind of travel around. They're born, and for a few frames, they kind of just make some noisy trajectory over the surface. Now, for each one of those particles, that won't be enough for us to create that type of arch effect. So we need, what we're going to be doing is, based on one particle, let's say we have a particle that's at a certain point in time, is somewhere around here. The goal is going to be for us, or my strategy is going to be for me to kind of calculate a random vector that's going to be tangent to the surface. So that point can have a normal. So let's say we have the normal pointing out of the surface, then we'll get a perpendicular vector to that pointing in this direction, and we'll throw a position somewhere along that vector. So let's say we're throwing it somewhere around here. And then we're going to be projecting it back to the surface. So what this is going to give us is, for every particle that's going to be traveling around the body of the robot, we will have a corresponding particle somewhere nearby traveling also on the robot body. And we'll then connect those two. Let me try to make this a bit more graphic. So we'll connect those two particles, and then we'll create the arch from that connection. Okay, so that's the main principle behind this strategy that I'm going to be taking. The first step is going to be for us to kind of just simulate some particles. So let's create a pop network. This will be our source. Later on, so this is time shift. Okay, go there. So pop network, and the creation frame can be, but yeah, they're inheriting the velocity from the surface. So we're gonna go here, and at this time we can just go to the attributes and say inherit velocity 0, and that way they're just being born. Next, we don't want them to last all that much. Okay, so I would say that maybe 0.3 and 0.15 is a good balance. And also for the scale and how the quantity of particles that we're going to be using, let's say that we're going to be using the emission attribute density. That's something we can use because it's going to be growing on the object. At this point, it's actually just static. It's not growing, but we choose a frame that's already has a good amount of density, and then we scale point count by area, and the number I've reached was 400. I'm gonna hide the guide, and we should see some particles being emitted and being killed immediately. So they're just being emitted on the surface. For us to better visualize the particles, let's see if we can have, let's go outside. Let's create a sphere. Let's say it's a primitive, and let's copy the points. Maybe just reduce them. This is all temporary, okay? It's just for visualization purpose. P-scale, and let's say, oh, better yet, let's not waste time on that. Let's just go to the sphere itself, and we can see they're being born and dying, but not moving over the surface. Okay, if we have a look at the surface, you'll see, not this one, this one. You'll see that they're definitely on the surface, but not going anywhere. So that's something we need to take care of. Let's do that with a pop force. Let's go to the pop force. And we can apply some noise to this. So let's say amplitude of 1 for us to start kind of nailing it down. Swirl size 0.5. And we don't need this to be very erratic. Let's start with 1 and see what this gives us. As you can probably guess, the particles will kind of now start going away from the surface, and that's also not what we want. So if we merge these, probably better. Let's merge these two. We have this and we have that. Let's give it some color. Can be blue. Okay, so they're kind of, some of them at least, drifting away from, I would say most of them, either going inside the object or just drifting away. Okay, not the goal, so let's dive inside. Let's fix it. Let's use a pop wrangle. Let's put it here, and let's call this attach to surface, or stick to surface. That's a better name. And all we have to do, let's make sure that the inputs, we map the second input to the second context geometry, which means that here we should have, oh no, we can just use the first context geometry. What am I thinking? So none first context geometry, or no, let's go with none, and here first context geometry. Okay, this means if I reference input 1, which is actually input 2, if I reference input 2, let's say like that, if I reference input 2, which has the index 1, I will be grabbing the geometry, and I can just say that P at P, my position is going to be equal to the minimum position on the second input based on at P. Now let's be more drastic about this force. Let's go with 2.5, and let's see what this gives us. We should see particles moving, but none of them going away from the surface. Okay? Could probably move a bit more. Maybe not pulse length. Let's increase the pulse length. Let's increase the swirl size. Let's try it with 1. Let's see what this gives us. And let's go with 4. Okay, so they're sliding across the surface pretty nicely. Probably a bit too much, so let's bring this back down to 3. Okay, cool. And it's cool they have that kind of acceleration effect. I like that. Okay, so first part of the problem is solved. So on the next lesson, we're going to be creating the second point, or the matching point, for each one of these particles.